see if you can share your slides with us.
Yes, I'm doing that.
And the title, yeah, maybe I would not tell the title because it will be on your slides. Well, go ahead. The floor is yours. Thank you so much.
Okay, thank you very much. Again, sorry to keep you waiting. Please do interrupt and ask me questions as we go along. I would prefer to do it dynamically. Thank you. So I'm going to talk about some joint work with my graduate student I-Hsun Chen and Juniper Cocomello and postdoc Sarath Yasodharan at Brown University. This is on quenched hydrodynamic limits for interacting jump processes on sparse random graphs. So let me just introduce the model and questions first. So of course, we, as all of you know, if you consider an interacting process, interacting particle system, it is simply a large collection of randomly evolving particles labeled by the nodes of a graph, which governs the dynamic interactions between particles. And the instantaneous stochastic evolution of the state of the particle is either directly influenced just by its own state and the states of particles in the neighborhood, or you could also look at more general non-Markovian interacting particle systems in which it could be influenced by its evolution history and the evolution histories of the particles in its neighborhood. Okay, can everybody hear me? Yes, okay, great. And in this talk, of course, the stochastic evolution can be of different types. It can be either a discrete time process or it can be a diffusion. But for this talk, I'm going to focus on the case when it's just a pure jump process. Okay, so I'll be more clear about that. And the common notation that I will use, of course, I will always assume my graph is finite or either locally finite, which means that the number of vertices that are in the neighborhood of any vertex is always finite. And I'll use NV to denote the neighborhood of V, which is just all the vertices in the which have an edge connecting to that vertex. dV is the cardinality of the neighborhood, just the degree. And maybe this is the only standard, slightly non-standard thing, which I will use V bar or CLV, which denotes the closure, that is V and its neighborhood, okay, of V and G. And I will, leave out G when it's implicit. And I will interchangeably write V and G or V and V. And given any some set S, which we think of as the state space, and you're given some configuration of the particles in this set of vertices taking each particle taking values in S, and any subset of the vertices, I'll just simply use XA to show the marginal the configuration of the particles in A. Okay. So now let's talk about sort of what is the setting. We could consider, for example, a fixed graph, some countable set. I'll always have a countable set here, and some initial condition. And you might look at a Markov process that evolves as a locally interacting Markov process. So jump process, right? Like just discrete time. So the probability that it takes some value Z at time t plus 1, given that it was taking value Y, since the whole thing I'm assuming is a Markov process, of course, in general, that could depend on the entire configuration Y in SV. But since it's locally interacting, what I mean by that is just that it only depends on the values in T of the vertex itself at time T and its neighborhood. Okay, so that's sort of the standard framework of interacting particle systems. So we can write this evolution in terms of, okay, it's something that goes from YV to Z. So it's some sort of transition probability matrix, which would be the usual Markov chain if just the individual particle was a Markov chain. But here, in addition, you have this dependence also on the neighborhood configuration. Clear? Okay, so your whole evolution is given by some collection of transition probability matrices, which are a family, which is parametrized by also sort of the vector of the neighborhood states. Okay, and of course, this vector could be of any length because, you could have your neighborhood large, right? So in a finite graph, it could be of maximum length, which is the maximum degree, right, of the neighborhood of any vertex in the graph. But so usually this dependence is always symmetric. So sometimes we can also think of it depending on the empirical measure of the states in the neighborhood. Okay, so I will use that also at some time, but sometimes it's useful to just think of it as sort of this vector of particles and not just the empirical measure, because then it also allows you to count the numbers of particles in your neighborhood rather than just the fractions that have a particular state. Okay, so this is just a just generic say setup, right? Okay. Okay. And you don't have to worry too much about this unordered finite sets. Just, think of them as just the configurations of the neighborhood. These sigma bars sigma vectors are just configurations of the neighborhood at some given time. Or what I will focus more on in this case is the continuous time Markov chains. So again, you fix a graph, you fix an initial condition, and now the state will evolve as a locally interacting continuous time Markov chain. So again, that will be governed by some jump rate matrix, okay? So in general, it could depend on the entire configuration at time t. So this is the rate at which I jump from state yv to some state z, right? If they were all independent, that would just be the way the Markov chain is evolving, some gamma yz. But now again, it could depend also on the neighborhood configuration. So here's a picture of the neighborhood configuration, right? That would be the vector. Clear? Okay, so are the states of the neighbor. And so now again, the dynamics of the particle systems are governed by a family of rate matrices, which are again indexed by these vectors in the neighborhood. Clear? Okay. So, but one might also want to consider not just Markovian, but one could also consider instead, you're not just looking at your state, but you're looking at your entire history. So I will use this to denote the entire past. That is these, this bracket. And this is to say that I'm not including T. And so similarly, and also all the entire past of the neighborhoods. Okay? Okay. So that's just a generalization. And we can also now do the same thing with the continuous time processes. Now, I will have a rate matrix that could depend on the entire past, the history of the processes in this thing. And I look at how I go from Z prime to Z. Okay? Okay, so this is just a general framework, and it's often more convenient to characterize the non-Markovian jump processes in terms of jump rates instead of these matrices, because now I just have Rj, which depends on the entire configuration of all the past histories of the neighborhood, including itself. Okay, so it's just an equivalent way instead of writing it in terms of, rate matrices that we do for Markov processes. You can think of it as a point process with some intensities along some jump directions. Is that clear? So my J is just equivalent to saying Z minus Z prime, right? That's the jump that I take. Okay, so this is all very general. Let's go with some concrete examples. So let's say the state space of each particle is, the SIR process, which many of you, I'm sure, are very familiar with, but I will just still quickly summarize. So you have three states. One, S is susceptible, so it's healthy and susceptible to getting the disease. I is infected, and R is recovered, which means it's healthy, immune, and no longer contagious, cannot get the disease. And then the transitions in this are governed by two parameters, beta and rho, representing the infection and recovery probabilities. So the rate at which in the discrete time you catch the disease, so you recover you go from I to R at a rate that doesn't depend at all on your neighborhood. Okay? So your I to R of rho is just some given rho. That's what this recovery rate is. It doesn't depend on your neighborhood. And so, of course, the probability, you can only go to R, you can't go back to S. So this probability is just the 1 minus that. But now if you go the rate at which you stay at S, then you have a chance of being infected by any of your neighbors. And so then it depends on the neighborhood, and it depends on the neighborhood in terms of the number of infected coordinates of A, right? So it's the number of your neighborhood, which has the value I, and this is the probability, the probability that you do not, none of them infect you, and it's all independently done. So this is the probability that you don't get infected. And of course, this is just 1 minus that. Okay, so just an example, the details are not that crucial. And we could do this in continuous time, where you again have two parameters, beta rho. So, and the family of rate matrices takes a similar form. You go from I to R in a way that doesn't depend on your neighborhood, and you go from S to I in a way that's beta times, it's proportional to the number of your neighbors which are infected. Okay, so one thing to pay attention here is you can notice that this rate can be extremely large if you have a high degree, right? So if you have a large degree, this could potentially be larger. Okay, so okay, and you could do various models that of epidemiological. You could add another state exposed and infected, but it's not yet contagious, and people do this a lot in models, and then you can have one more parameter, and you could also allow the beta lambda rho to be time varying. And so I'm just telling you that you can have, quite a general framework that you can include. Okay, so often one wants to look at time varying rates to capture seasonal variations and things like that. Okay, and so here again, E to I to R doesn't depend on your neighborhood, only S to E does, and that's given in the same way as before. Okay, so the question is, what are the quantities of interest, right? So what you are is you're given some graph, some initial conditions, you're given some jump rates, and let's say that you have a well-defined associated jump process that satisfies these initial conditions. We are interested in a sort of macroscopic descriptions of the process. So it could be like the fractions of particles in different states. So here's just could be the global empirical measure on trajectory space, or you could fix at a particular time and say, what is the fraction of particles in any state at that time? So, right, this would be a probability measure on trajectory space. So it would be in discrete time in S infinity, and in continuous time, this should actually be D, the space of sort of Cadillac processes or piecewise constant property. This should be D, yeah. Okay, and similarly here, it could be in S, or, it would always be in S. So this was sort of for the diffusion case, you allow C and R. Okay, and so these capture averages or nice functionals of the paths, right? So, so that's what we're interested in. Okay, but what are really the questions? So of course, there's been a lot of work on interacting particle systems, but we're taking sort of a view of trying to understand asymptotic limits of these particle systems in the following way. So if you're given a sequence of graphs with the number of vertex size going to infinity and some appropriate initial conditions, you might ask, what is the typical behavior of the global empirical measure for graphs which have a large vertex size, right? So of course, that's very complicated. And so you don't expect any exact expressions for, what mu g and xn looks like for some large complicated graph. So you might hope for some tractability being recovered as you send, things to infinity, the particle size to infinity. So, which is probably something that would be non-intuitive to anybody but mathematicians and probability, that you send things to infinity and you will get, more tractability. But okay, so you get, does mu g and xn converge to some limit mu? And does a typical particle, so this is just some particle in the system that you take, maybe you choose it uniformly at random from all the vertices in the graph, does that converge to some limit process? Okay. So you might be interested in your evolution, as in the epidemics, do you get infected or not? Or just what is the whole population doing, macroscopic sort of questions. And if you do that, if so, can one obtain a tractable characterization of the limit? I'm not going to talk too much about this question. I will just mention it at the very end. We have studied that, but that's not the focus of this talk. And then the other question, question 3, is can one characterize, if you do have question 1, you know that you have some typical dynamics, then can one also characterize large deviations of this global empirical measure or the empirical measure flow? By that, I mean that you want to understand, okay, maybe typically it goes to mu, but what is the probability that it might actually be in some other set that does not include mu? Right? And you might expect that you have sort of an exponential decay. You know that that goes to 0 if A does not contain mu. And you often want to understand if there's some exponential decay rate. If so, what is the speed and what is the rate function? So this IA is a short form for this inf of a rate function I, which is taking probability measures on S or S infinity, whether it's trajectories or states, to infinity, to the rate function. Is this clear? Okay, so you want to ask large deviations and understand whether we can compute this rate function. In this talk, the speed is going to be pretty much the natural one, so there's no surprises there, but we're going to find out if we can understand what the rate function is. Okay, so just to get some reality check whether these are reasonable questions to ask. So let's look at a trivial observation. So suppose you had non-interacting Markov chains with some jump matrix. Okay, so now here, this jump matrix is, of course, not even depending on your neighbors. Okay, so then does x, gn, xn, so now you have n particles, all of them are not interacting. Do they converge to a limit? Of course, they converge to an infinite product measure, right? And with each marginal is equal to just the evolution of the first particle. Okay, so this is a trivial observation, as I promised it was trivial, right? Okay. So it doesn't really depend on n at all, right? Each particle's evolution. And now you can ask, okay, does mu gn xn, the global empirical measure, does it converge to some limit, mu? That's also trivial, of course, by the strong law of large numbers in general. You would expect mu gn xn to converge to its mean or expectation. So mu gn xn converges to mu, which would be just the expectation. So here I'm just sending the number, the graph size to part. So the number of vertices to infinity in any way. And so would be just the expectation of the delta mass at any one particle because of exchangeability, because all of these are exactly the same. So if I take the expectation of this, it's the same as 1 over n times that of the expectation of the delta, just strong law of large numbers, which is in fact just the law of any one particle. And of course, we know how the law of a Markov chain evolves. It's given by this linear ODE. Right, so for instance, if you have a finite state space, it's just a really linear ODE on the simplex. Yes, just a Kolmogorov equation of the Markov chain. Okay, so okay, and then can one automatically characterize the marginal dynamics? Yes, it's trivially the dynamics of a continuous time Markov chain with rate matrix gamma, and we know that the law is this. Fine. And now, can one characterize the large deviations behavior, right? Okay, okay. And yes, I'm sorry, it's gone below, but that's given by Sanov's theorem on general Polish spaces, right? So because these are just, you're taking something which is an IID copies of just a Markov chains, and Sanov's theorem is a general result on averages of IID random variables on general Polish spaces. And that tells you that, in fact, this does satisfy a large deviation principle with a rate function that is simply relative entropy of whatever measure with respect to the typical one, which is the mu. Clear? Okay, so we know all of this, so it's all reasonable in the uninteresting non-interacting case, but at least we know that that's a reality check. So let's consider now a more classically studied problem, which is in the case of a dense or a mean field regime. Okay. So in this case now, so there's actually some kind of interaction. So in this case, it's the same as saying I take my underlying graph to be the complete graph. And now, because the family of rate matrices, remember, depends on the configuration of the neighborhood, and due to symmetry, you can sort of assume I just have to look at the empirical measure of the configuration in the neighborhood. I can also treat this as just being a rate matrix of the form, some probability measure on S, and this theta you should think of as the empirical measure of the configuration in the neighborhood. And for simplicity here, I'm just simply doing the Markovian case, okay? But I will explain that. Okay, then there's classical mean field limits, for instance, going back to Ulschlager in 1984, but there are many, many other versions, Ben-Haim, et cetera, et cetera. So it says that if you have some nice conditions on the initial conditions, exchangeability or some convergence, even this is enough, then indeed any one particle will converge to a limit, the global empirical measure, which I now just denote by mu n instead of mu gn, because I've set g to be kn. And of course, this mu will coincide with the law of x bar, just as in the non-interacting case. Yes? So you have the global empirical measure limit and the law of a typical particle coinciding in the limit. But now, of course, the limit solves a nonlinear ODE, where your d mu by dt is mu t gamma t mu t. If you remember, the rate matrix that you had, right, for the n particle system would be, in fact, gamma t of mu n of t, right? So, of course, I haven't stated the exact conditions on gamma. You need some conditions on gamma for this to work. But if you have gamma, which is continuous in this, nicely continuous with respect to this, this variable, then you know that your mu n's are converging to mu. And so you expect gamma t mu n to converge to gamma t mu. And of course, then the forward Kolmogorov equations tells you that this should be this. So of course, this is classical and known, so I'm not spending too much time on it. But what we do know is that X bar is a nonlinear or a measure-dependent Markov chain, right? Nonlinear because the ODE is now nonlinear, where the rate matrix itself depends on the law of the process, right? And the typical X bar is just a process that evolves like this with a rate matrix that depends, it's an inhomogeneous Markov process, which depends on its own law. Yes, any questions? Okay. So this is classical. So of course, so what do we have? We said, does the law now in the, key questions in the classical, but slightly non-trivial case, but by now well-known. Yes, the law of X1n has a limit. But the key thing is, this is a consequence of the exchangeability of the particles. Really, that's all that you're using. So you're using permutation symmetry of the joint law. Okay. And then does the empirical measure have a limit? Yes. And here, we said that, of course, you have interacting particles at finite n, but the influence, since is of all other particles on any particle, is only through the global empirical measure, right? And so therefore, which is scaled as 1 over n. So any one particle influences the other particle only of order 1 over n. And that's going to 0 as n goes to infinity. And so in the limit, any two particles or any finite number of particles are asymptotically independent. And so that's why you have that the global empirical measure is once again going to something that is deterministic, and if it's deterministic, it has to coincide with the law of the X bar by exchangeability. Okay, so it's sort of the same strong law works, except you have weakly interacting particle systems, so you have still the same thing, and you have this, and what guarantees that is this asymptotic independence, which is also called propagation of chaos. Okay, that is you're assuming something, the same thing on the initial conditions, and you get that in the limit as n tends to infinity. Okay. And then, of course, we had the question, can the law of the dynamics of a fixed typical particle be autonomously described? And I said yes, in terms of the nonlinear Markov process. Clear? Okay, and now can one describe the atypical behavior of mu n, mu k n, xn? So can we find some sort of rate function here of this form? So it turns out that if you look at how mu kn, let's just assume for simplicity that you're on a finite state space, then you can actually write down mu n kn itself is a Markov process, because remember that the rates only depend on mu n itself, right? So you can look at mu n kn xn as a sort of Markov process, and then you can apply known results for large deviations for Markov processes to do this. There are many ways of proving this result. But yes, under suitable conditions on the jump rates and initial conditions, it's classically known going back to work of Kurtz in the 70s. Then there's been lots of people who've done works on, including many in this audience, who have done works on large deviations and even more refined large deviations for jump Markov processes. And the mu kn xn itself is just a jump Markov process, and you can sort of solve this. And you can also allow simultaneous jumps, and then you can allow countable state spaces, etc. And there are different representations for the rate function. But one form that's useful to just keep in mind, just to show that relative entropy comes in again, is sort of, what is this? I'm looking for how much my rate function is something that is a function of probability measures on my state space, right? And my state space is that of trajectories. So it's a probability measures on trajectories, right? And we know that it should actually be 0 at the typical trajectory, right? Which is your mu. And because that should have probability 1, and so, you remember IA is just the inf of all of these, so you should have 0 here in order for this to be 1, right? Because IA is a non-negative. So it turns out that you can write this I pi as h of pi theta pi, where what is theta pi? Theta pi is sort of the law of the same particle dynamics when you freeze your mean field influence at pi. Okay, so I've just written what this thing is, a mean field ODE with frozen environment. The details are not important. I just wanted to mention that once again, you have something in the form of relative entropy. Okay, and why is that the case? Because you had, so this H is the relative entropy functional, okay, between two measures. And of course, this is true only if pi is absolutely continuous to theta pi and 0 otherwise, right? So, and it's easy to see that, in fact, this mu satisfies, we knew before, d mu t is gamma t mu t. So it's actually a fixed point of this mapping, theta pi. And that's why we know that the h mu of theta mu will be h mu mu, which will be 0, right? So that's a reality check that indeed, the rate function is 0 at the typical particle. Okay, so at least in 2 cases, we know that you get all of these, you can answer all of these questions, okay? And there is a lot more work that people have done in the dense graphs, not quite complete graphs, which have some similar results, but I don't have the time to get into that. So one question is, okay, do mean fields approximate? So it seems like we know everything. And then, many of these results have been extended to sort of dense graphs. By dense graphs, I mean sequences of graphs in which the minimum degree or average degree, depending on different models, goes to infinity as n goes to infinity. Okay, in that case, you still have the influence of any one particle on the other is still inversely proportional to the degree because of the symmetry condition. And so if that's going to infinity, you still have sort of decay of correlations, and you have this propagation of chaos, and everything sort of works out, but it's much more complicated in the dense case, but because you don't have the same kinds of symmetries, but it is not fundamentally a different limit or a different analysis, right? Okay. So now the question is, okay, since these arise in many cases, do we expect mean field approximations to work well on any graph? And so here we look at the discrete time SIR process on a ring, on a cycle or a ring, which I think of size 200. And now we see the plot of the probability of being healthy versus time. And the mean field approximation is this green one. And the actual simulation is blue. So we see that, of course, the mean field approximation is not good on the ring. You can also do, I didn't, explain what the voter model is, but many people know that. So another kind of interacting particle system, you can look on the tree, a rooted 3-regular tree. And this is the probability that the root vertex of the tree agrees with 2 of its neighbors, exactly 2. Just some arbitrary functional that also involves the neighborhood. Okay, you could choose other things and you get similar kinds of results. And again, the mean field is in blue and the simulation is very different. So the mean field doesn't track it. And of course, the mean field won't track something that looks at correlations, because we know that the mean field assumes neighboring particles are independent. So you might say, oh, I should do a more refined approximation that also somehow takes into account correlations. People have, in statistical physics and other disciplines, have introduced something called pairwise approximation, which is sort of an ad hoc approximation. And so you can just run that and see if, there's not a theory there always. So, but you can run it and see if it's doing well, and it's clearly not doing well. So it does better in the beginning, but after that, it again does badly after a certain point. Okay, it doesn't track the simulation. So this really motivates going beyond mean field approximations and their refinements. And so instead of looking at the complete graph or dense graphs, we want to look at sparse graphs. So what I should really say is sparse graph sequences. And by that, I mean, I want to look at graph sequences where the degrees of vertices, let's say the maximum degree, remains bounded as the vertex size goes to infinity. So it remains uniformly bounded, or the maximal average degree if it's a random graph. So here's sort of an Erdős-Rényi graph with some parameter p over n with n. Okay, so then the average degree is p, and it remains p. And if you look at the sequence, and I want to understand dynamics on this. So there are 2 reasons why you would be interested in the sparse, because many people who have looked at real-world networks, many of them feel that actually many real-world networks are sparse, or at least have a degree of sparsity. For example, if the population of São Paulo goes higher, it's not, your social circle is not going to increase proportionally, right? You sort of remain, unless you are a real extrovert, you're going to remain sort of bounded in terms of how many friends that you have. And so your social contact network remains the same. So this feature of having sparse graph sequences that you have to understand is something that appears in many applications. And so we want to look at that. And you want to characterize both typical and atypical behavior of the global empirical measure for sequences of such sparse random graphs. Okay, so let's move to that main point. So let me quickly think about what are the challenges. So remember, so for example, you can take as your sparse graph sequence the Erdős-Rényi graph with some gn c over n if you want, throughout as a. And the study of dynamics on the sparse graphs was, for example, posed as an open problem in the Latre, Giacomin, and Lusson back in 2000, around 8 years ago, 10 years ago, or 8 years ago. So if you look at these challenges, what are the challenges? How is it different from the complete or dense graph setting? So first, notice that, of course, neighboring particles will no longer be asymptotically independent, right? Because the influence of any particle on another is inversely proportional to the degree. The degree is remaining bounded, so it's going to be of order 1. It's not going to 0. Okay, so there will be no propagation of chaos for, neighboring particles. The second thing is, even if somehow miraculously I found the global empirical measure, the interaction between particles is through the local empirical measure, right? It's through the local neighborhood. So the knowledge of the global empirical measure will not, even if I have all the continuity I want and the jump rates, it's not going to tell me how an individual particle evolves. Is that clear? Because the individual particle is evolving according to some rate function, which depends on its local neighborhood, which remains stochastic in the limit. Okay, because they only have finitely many particles influencing you. So therefore, that's another thing that's a problem. The third thing is that you cannot expect a limit by just taking the number of particles to infinity, like we did in the graph, in the dense case, or even complete graphs case, because clearly the graph topology is going to matter. So, for example, because of the fact that you're strongly interacting, the structure of your neighborhood is going to matter. So if you look at a 4 regular tree, that's going to be different from looking at the lattice, 2D, 2-dimensional lattice, like the dynamics on the 2-dimensional lattice and the 4 regular tree, though everybody has immediate neighborhood exactly 4, the degree of every vertex is 4, this topology, if you go later, is going to matter, okay, because of the strong interaction. And that's actually what makes this regime interesting, because then you can ask question on how does the dynamics depend on this topology, right? And that's what you want to sort of capture. So of course, the first question is, okay, if I can't just send the number of vertices to infinity, then you want to consider a principled way of looking at graphs with different vertex sizes. So as the vertex sizes goes to infinity, I have to choose a sequence of graphs that somehow preserve the local topology, because we said that the local topology matters. And luckily, we know of, so this has been around for 20 years, this notion of local convergence for sparse graphs, which essentially is saying exactly what we want, which is saying that you have a sequence of graphs that converge locally to a limit graph, G, if for every finite k, the k neighborhood of one graph is isomorphic to the k neighborhood of the limit graph. And now I should emphasize that these should be rooted graphs, because otherwise, what do you mean by k neighborhood of something? So when you take a root, then you can talk about the neighborhood of that root, right, with respect to the graph distance, and you want those two to be isomorphic. Okay, for every k, the n that you have to go beyond here could depend on k, but you just want to make sure there's always some nk such that it's isomorphic. Another way to look at this is just to understand through a picture is that, okay, the cycle graph will just converge to the infinite line, because locally it looks just like your neighborhood for any k is going to look exactly like that in the line, okay? So I'm not looking at the global, but only any finite, and I can take n large enough such that I don't see the cycle, yeah? Okay, another way of sort of formalizing this, which will be important in the large deviations, is we're going to consider the class of sort of unlabeled rooted graphs. So let's understand what that means. So I take G, which is a finite, locally finite labeled, meaning labeled with the vertices. I just put some numbers 1, 2, 3. And G denotes some unlabeled connected graph with a distinguished vertex, which we call the root. And BRG is, of course, like I said, the R neighborhood of that root of that rooted graph. And so now I'm going to look at only, so how do I connect a labeled graph to sort of unlabeled? It's just through sort of isomorphism classes. So here, let me just give an example. If I have the following graph 1, 2, 3, then really, if I look that from the point of view of the root 1, and I choose this root sort of uniformly at random here. So if the root is 1, then my graph looks like this, right? But if my root is 2, it looks like this. And also if my root is 3, it looks like this, because I can just flip it through an isomorphism, okay? So then with probability 1/3, I will have this graph, and with probability 2/3, I have this graph. Okay, is that clear? So I have a fixed graph, which is maybe labeled if you want. And then, so G star is the space of unlabeled rooted connected graphs. You can also think of it as sort of isomorphism classes of rooted graphs. Okay, but I just thought an explicit example could be helpful. Then you can put a certain metric on it. The importance of this particular metric is not important, but then you can calculate, for example, the distance between these two graphs. And G star under this metric is nice, complete, and separable. And so you can also consider the space of probability measures on G star, like equipped with the usual weak convergence metric, taking values in these random graphs. So we can now talk about random graphs having convergence in this space. Clear? So you have a nice Polish topology. That's all we're saying. And now one thing that's of interest is the component empirical measure. So let me just explain what that is. So again, I consider a graph G on N7 vertices. And CV of G is just the connected component of the graph rooted at V. And now I define UNG. It's going to be a measure on graphs, right? This from this isomorphism classes of graphs. So I will put a Dirac delta mass depending on which component I'm at. But remember, these are rooted graphs. So let's just see what will happen in this example. So with probability 2/7, I may get this vertex or this vertex, in which case my graph will look like this D. Okay, it will look like this. But now if I choose the center here, there's only one way that with 1/7, I would choose the center, and then my graph would look like B, right? And then you can see, okay, if I choose this end, it'll be the same as choosing this end, and I would have something like A. And if I chose this elbow, then I would have, again, 2/7 probability. It would look like this, okay? So you have different rooted graphs. So from the point of view of the root, these four graphs, all these graphs look different. I just looked at the connected component. And so I have this component empirical measure that you put, which is a probability measure on the space of graphs, okay? And then the convergence in the local weak sense can be, formalized in this way, but you can just think of those pictures and more pictures that I will draw, but you can you can say that a graph sequence converges to a limit if UN goes to row weakly in the sense in distribution. So with this, and it's slightly stronger if I don't take an expectation here, but I want this to converge to this in probability. Okay, so again, just that there are two versions of this, depending on how strongly UN converges to some limit graph. Okay, so again, so let me just give examples. So suppose you have a uniform random regular graph. You take all graphs with n vertices that have exactly degree D. Okay, I mean, there's a compatibility condition between n and D that's needed that I'm just ignoring. And then I select one uniformly at random. Okay, so that's because it's a finite set of graphs which have, n vertices, and with all vertices having some degree. And then I place the root at a randomly chosen vertex. So then I get a rooted graph, and I get a randomly rooted graph. And this converges in probability in the local weak sense to the infinite D regular tree. This was proved back in quite a while ago, 40 years ago now. And so what is surprising about this result, this is, the cycle to the line was a pretty trivial result, but here it's somewhat non-trivial because you know that the random regular graph has many cycles, right? Like the triangle is a random regular graph, two regular graph, right? So you can have cycles, but what it's saying is that somehow what this local weak convergence is saying, that the probability of a random vertex seeing a small cycle is going to 0. In the limit, you can still have cycles, but the probability that you see it as the large size goes to 0. Okay, so that's sort of intuitively. So these are often called locally tree-like graphs. And the Erdős-Schwenny graph that we talked about earlier, which is like C over N, or more generally, some NPN converging to P or C, will converge to the Galton-Watson tree with offspring distribution Poisson with the same parameter P. Okay, and this Poisson is arising from the fact that locally the number of vertices of yours is, of course, a binomial NP over N. We know that looks like Poisson P in the limit. Okay, law of rare events. Okay, so Galton-Watson tree, you start with a root, have Poisson offspring, and each of those offspring, again, have Poisson, independently, and so on. So that's an infinite tree. And again, you can see that this Erdős-Schwenny, even though it's sparse, has many cycles, but in the end, you go to a tree. So there are many other examples, the configuration model, preferential attachment, etc., and all of them converge to random trees many times. But of course, a lattice, finite lattice, also converges locally to an infinite lattice, and that's certainly not a tree. Okay, but many random graphs converge to random trees. Okay, but I also want, because we're considering sort of dynamics, we also need to mark the graphs with some initial conditions, right? Because you can't just say the graph converges and then my dynamics converges. I also need to make sure the initial conditions converge in a suitable sense. So don't worry about the details of this. This is just to be, complete. But you can mark the vertices with your initial conditions. Then you can evolve the whole dynamical system, and you will get trajectories if the dynamical system is well posed. And then you can look at the random graph marked with these trajectories. And so now you have two sequences of marked graphs, and you can ask, if this one converges, does this one converge? Okay, is that clear? Okay, So if the graph itself converges and you just use some IID marks for the initial conditions, then it's always that will also converge to the limit graph with the same IID marks. So for simplicity, let's just assume we're doing IID initial conditions. One can do more general things, but that's fine, okay? Okay, so you have similar notion of local convergence for marked graphs. I don't want to go into that. So now I can refine my statement. We've just spent a lot of time saying, what is even the notion of convergence that you must use to even ask our questions? And so first, I'm going to say that I'm going to really represent the dynamics as a jump SDE rather than in terms of these rate matrices, because that's more useful in the case when you are looking at non-Markovian processes rather than rate matrices. So even a Markovian SDE is really driven by these exponentially distributed random variables, right? Continuous time Markov chain, which can be generated from a Poisson process. And so it turns out that you can write these as a solution to a jump SDE where these NVs are certain Poisson random measures. Okay, so I'm not going to go into the detail of this representation because either you've seen it before and you know, or you don't. So you just have to take my word that, you have, just like you have diffusions that are driven by Brownian motions, similarly, you can write these jump SD non-Markovian jump processes as being driven by independent Poisson processes at each vertex, okay? And based on some rates. The rates will depend on time. They could depend on time. They'll depend on the vertex neighborhood and also the past of the trajectories. Or if we do Markovian, they'll depend just on the current state of the trajectories in the neighborhood. Remember, V bar is the closure. So itself and its neighborhood. Okay, clear? And it could also, when I say V bar, it's also depending on the graph structure of the neighborhood because I need to see how it's sort of connected. Okay. So these rates are a function of the graph structure and the marks on it, which are these trajectories representing the histories. Okay. And so then we ask the question, if you have GN that converges in the local weak sense, GN equipped with its initial conditions, etc., and you converge to a limit graph, then does that same graph equipped with the associated dynamics also converge? And does the empirical measure converge? Yeah, okay. So let me now get to the results. Any questions so far? Okay. So we want to, like I said, we will view the transition rates as function of one marked stars. So just the neighborhood, one neighborhood of the vertex, so which will look like a star. I don't care about connections between my neighbors. And that just captures the root neighborhood marked with the states and histories of the process. You can just think of the states of the process in the Markovian case. And so this space will be just marked stars. T star 1, X is the equivalence class of marked star, which is just telling you how many neighbors you have. Really, that's all you have. And now I make some generic assumptions on the transition rates, which are quite general, that there just exists some constants such that these rates, remember, that can depend on the graph structure or your marked star here, and it can depend on trajectories in your neighborhood. They should just be less than CK. So if my neighborhood is of size K, it should be less than or equal to CK. That's it. So I'm allowing my rates to grow with the neighborhood, and I'm not saying how the CK should depend on the neighborhood, whether it should be linear or nonlinear. That's okay. I should just have some CKs. And this is really important that I have to allow these rates to grow with the neighborhood because we know that that happens, for example, in the SIR process, right? Because the more neighbors you have, then the rate at which you can increase is going to be larger because you could have more infected people in your neighborhood. Okay. And then there's if you also want to assume non-Markovian, you have a mild continuity property. Let's ignore that for now. Okay. So this, for example, this continuity property is trivially satisfied in the Markov case, so we can just understand what's, so all you want is just these rates having this bound. So it's a degree-dependent bound. Then in work with Ganguly and Ramanan for Anukam Ganguly for the continuous time case, and the discrete time case was done earlier here, which is much simpler. If the graphs marked with initial conditions converge in distribution in the local weak sense, and the graph, the limit graph G, has a certain property called finite dissociability, which I will tell you about in a minute, then the graphs marked with the trajectories also converge in distribution in the local weak sense. Okay? Okay, so now we have a general result that, okay, in particular, so we have shown that actually the limit of any randomly chosen, the root particle of the graph will be the marginal of the limit of the dynamics on the infinite tree or the infinite graph G. Is this clear? So one of our questions was, does a typical particle have a limit at all, right? The dynamics of a typical particle. We're saying yes, if the GNs converge to some limit G in this local weak sense, then we run the dynamics on the limit graph and we look at what the dynamics of the root particle is. That's exactly what this converges to, that process. Okay. Now, of course, you might say, okay, originally I had the root particle as being the marginal of something on an, on a finite graph, and now I'm characterizing it as something on the marginal of an infinite graph. So how does it help? But it turns out that that allows you to do some nice autonomous characterizations of the graph, but I won't get into that right now. Okay, but the point is that there is a limit. And the second question that we had in the dense graph setting was, now what does the empirical measure look like? But before I go to that, let me tell you some challenges we had in the continuous time setting. What is this finite dissociability condition? So in the jump, SDE may actually, even with those conditions that we put on the graph, then you can ensure that the SDE on an infinite graph is even well posed. Otherwise, this SDE over here right on top may not even be well posed, even with that assumption. They're very simple examples. Why is that? Because you have an infinite graph. If your graph has finite degree, then you're okay. I mean, or rather, not finite degree, but if you have uniformly bounded degree, then you're okay. But if you don't have a uniformly bounded degree, you could be having a lot of sort of jumps in the Poisson process. So you cannot do a recursive, how you generally construct jump processes by just looking at the first jump and the next jump and the next jump and just sort of evolving the process. But there may be no first jump if there's sort of an accumulation point of jumps, and that can happen on an infinite tree with unbounded degree. Okay, unbounded maximal degree. And so you need this finite dissociability condition in order to in order to verify that that doesn't happen. And we did show that all Galton-Watson trees with finite mean distribution have this finite dissociability property when we have this condition. So for the graphs we care about, this limit holds without having to worry about the finite dissociability. Okay. So now the convergence of the global empirical measure. Note that there's no reason to even think that the global empirical measure should have a deterministic limit. Because remember, in the dense graph case, we said that's true because they're weakly interacting particle systems. So you sort of have like asymptotic independence and you have the same thing, right? But over here, you neither have sort of an exchangeability in some sense, and neither do you have strong correlations. But still, miraculously, you have this mu Gn go to here, and in fact, it coincides with the law. Okay, so this was just the empirical measure flow, or this is so this is also the neighborhood of the. I'm interested also in the global empirical measure, not just at a point, but also the point and its neighborhood, because when things are strongly correlated, I also want to understand correlations between particles and not just the asymptotic marginal of a particle. So I'll just take 5 minutes more if that's okay. Yeah. Okay. So that's any questions on this? So the question is, you might ask, why do you still get a deterministic result if you don't have any sort of asymptotic independence? And the point is that even though neighboring particles don't, if you choose two random particles in the graph, their neighborhoods, or finite neighborhoods, tend to be are asymptotically correlated. So the proof is some asymptotic correlation decay property where you don't take immediate, like you don't have propagation of chaos in the usual sense, but you have it for sort of randomly chosen particles, and then you use asymptotic correlation decay and a lot of estimates to show this. Okay. Okay, so now let's just get back to the IPS, and I will conclude with just telling you a little bit about whether we expect large deviations. So we know that there's some typical dynamics. We know it goes to the same law of the marginal of the root process in the limit graph, right? So we know that the global empirical measure converges. Can we understand its large deviations? Is that clear? So we have this dynamics right at the top, and then we have this neighborhood empirical measure over here. And so, I put a delta mass at the trajectories of the vertex and of its neighborhood. And the question is, I want to know what is the large deviation principle. And so, as is my usual rule, I try to step back. And because, now that mu is not a Markov process, I can't use any of the things that we did before for dense systems or complete graphs. So things are much more complicated. So what can we do? Remember why mu is not a Markov process, because how it evolves depends on how the local neighborhood empirical measures evolve, right? So I can't just evolve it based on what the global empirical measure is. In the complete graph, it was only depending on the global empirical measure again, and so it was Markov. Okay, so the fact that really the dynamics depends on the local and the global empirical measure is different makes this more complicated. So I go back, I step back and say, can I even prove this neighborhood empirical measure convergence in the non-interacting case? Okay, so let's look at this. We have each yi, so let's now just forget about the dynamics completely, okay? And I just want to convey this to you and leave the rest for it. So we forget about the dynamics. Now you have just a measure on, we're just interested in probability measures on these stars, right, with marks. Their IID, take from some discrete set, even take 0, 1 if you want, okay? Okay, and now I have this IID on some nice discrete space. You have the marked neighborhood empirical measure. If we were only interested in the root, then of course, this would just follow from Sanoff's theorem, and you would get relative entropy. But however, if you look at the neighborhood empirical measure, then the neighborhood empirical measure at this red root is going to be these vertices, and the one at this blue vertex is going to be these vertex. So there's overlap between, and quite strong overlaps between different vertices. So now you're looking at a sum of Dirac delta masses at dependent random variables, where the dependence depends on the underlying graph structure, right? So a priori, you cannot, you have to sort of think of how do I handle this? Okay, so the large deviations results are with work with I-Hsun Chen and Sarath Yasodharan. And let me tell you what sort of graph, I will take particular kinds of graph sequences. One is the sparse Erdős-Schwenny random graph. You can fix with that, but we can also consider some others, and don't worry about that. Just think of sparse Erdős-Schwenny random graphs. Okay, so we mark each vertex with IID marks with some law nu, and we denote the resultant marked graph by GNXN. So beautiful result by Caputo. Okay, this was studied by Caputo-Bordanov, and I'm going to explain that to you, but I'm first just stating the result, and then I will tell you how our work relates to that of Bordanov and Caputo. Okay, so the result here is that the sequence of these component empirical measures satisfy an LDP on the space of probability measures on graphs marked with, with marked space S, with a rate function that looks like this, where H is, as usual, relative entropy. Okay, so let me explain what all these things are. Rho H, so now remember that the limit thing is, rho is always supported on trees, which should not be a surprise because we showed that at least the law of large numbers limits of all these graphs goes to trees. Okay, so it turns out you could be in general, as GN goes, the large deviation rate function, maybe put some positive measure on things that are non-tree-like, but it turns out that that's not the case, that the large deviation function also, is supported only, it's only finite for graphs which are trees. So even if I deviate from my, limiting Galton-Watson tree, I still have to be another tree. Okay, not necessarily a Galton-Watson one, but I have to be another tree. Okay, and rho H over here is just the marginal of that tree up to the H neighborhood of the root. So I just sum over a bunch of relative entropies. The difference here is this, I have to tell you what rho H hat and rho H sort of check are, but this is really the structure that it is. And I will tell you, I will define that later. So in particular, this LDP holds for random regular graphs, holds for, ER graphs, etc. So rather than go into the definition of this rho hat check and rho hat, I just wanted to say again, relative entropy comes in, right? And we have a quite explicit form of the rate function. That's the whole point of showing you this expression. But rather than look at the whole component empirical measure, I will tell you what the LDP is for the neighborhood empirical measure, because there I can tell you what the hat and check things are more easily. And that'll give you a sense of what's going on. So this family of just the neighborhood empirical measure, so I'm not looking at the whole component, but just my neighborhood empirical measure, which will be focused on one trees, right? My neighborhood looks like trees because just basically 1 stars, marked 1 stars, right? It's a probability measure on marked 1 stars. And the rate, the large deviation rate function is exactly of this form. So it's just the sum of the relative entropy of mu with respect to a certain conditionally independent version of it. And this mu hat, I will tell you, is another version of the mu. Okay, and this just comes from the contraction principle from the general theorem. So let me just define mu hat and mu check. So this mu must be symmetric. That is the way it looks on the mu is symmetric on 0 and its leaves. And this mu hat with respect to the usual nu is just like, so the mu, the mu check, you can take, remember your original graph, which was the true law, is IID nu on all these vertices, right? So, but if I'm given a mu, I take the law of any one of the trees, of the leaves, and I mark the leaves with that, all independent with that law. So I make them independent. Mu itself, they could be correlated, but I make those marks independent. And in mu hat, I make them conditionally independent in a way. Okay, so I get 2 new mu's and mu hats from the original one by making them independent or conditionally independent. And the root mark is always the original root mark nu. And then you just take the relative entropy, and that's what your rate function is. So I should just quickly say that the prior works by Bordenave and Caputo had an LDP already for this kind of component empirical measure in the case of unmarked graphs. And then it was defined in terms of this sort of rather complicated expression on microstate entropy. Delgosha and Antaram extended that to marked graphs. Baldasso et al. Showed this LDP for various classes of graphs, all of them but had a very complicated form of the rate function. And so really what our work was in actually getting this tractable rate function in terms of relative entropies. And I will end with saying why that was useful. So there are many things that can be done once you have this more tractable form, including what are called Gibbs conditioning principles, which allow you to show what is the most likely way in which a rare event happens, for example. And so we have this in a paper of mine with Sarath Yasodharan and myself, which is on arXiv. So just, so the other application that you have to this is that you can actually then use this to get a quenched, so I said that you have this IID marks, but we really wanted to understand the large deviation principle for the interacting particle system. And so it turns out that you can get that through the fact that you can mark the graphs with the initial conditions, which are IID, and the noises, which are IID. Then you can look at the mapping that takes the law of that graph to the law of the interacting particle system. And you can show that it's continuous. So there are various subtleties over there because this mapping is not defined everywhere. And we use this rate function to show that you can ignore the place where it's not well defined. And then you can show that it is continuous. And then you get the rate function from the IID rate function by our contraction principle. And so an immediate corollary by concentration results is that, now you remember that we had this hydrodynamic limit that if you take a random graph and you're sort of taking the average over the graph structure and the dynamics, it converges to the limit random system, right? The law of the particle in the limit graph, where again, you're averaging over the graph structure. That's called an annealed limit. But here, what we say, if you take realizations of the graph and you take the dynamics on this, then almost surely you will converge also to the realizations in the limit graph, which is much stronger for applications, because in an application, you might have an actual given graph. And you want to say that I want to look at what the empirical measure looks like. You don't want to average over different graph structures, right? So you want to say, okay, that graph, can I approximate it by something? So I will end with, so this, I said we get this LDP for interacting particle systems, but I just want to say what we can say from this for the SIR dynamics on realizations of random ER graphs. So in work with Juniper Cocomello, we actually a way to characterize the limiting dynamics for annealed random graphs. And here we just have plots of realizations, various realizations of ER graph. And the blue is simulations, and the dotted line is really showing you, just look at the blue lines, because the others are for different states. So the blue lines are telling you how the susceptible evolves with time. And you can see the dotted line is exactly the limiting dynamics that you get from our hydrodynamic limit. And you can see that for different realizations, so it's really a quenched result that it matches so well. Of course, there are some like this, the fifth one and the right one in the middle where it's not so good. There are obviously some cases, and even this one down here. But for many realizations and almost all realizations in the limit, you actually have quite a a very good approximation. So just to summarize, and sorry for going a little over, so we just have sort of a new framework for rigorous asymptotics of marginal dynamics of interacting particle systems governed by sparse graphs. I should mention that in the interacting diffusion case, Baldasso et al. Had large deviations for gradient diffusions. So this is really looking at the jump process level for a general class of possibly non-Markovian jump processes. And I didn't talk much about what the autonomous characterization is of the dynamics, but that's actually certain conditional Makin-Vlasov processes for people who know what that is. And the marginal dynamics is in general non-Markovian, even when the whole process is Markovian. So this is quite sort of a new class of processes that one wants to analyze. So maybe I will just stop by saying we can also allow random environments, but to keep this talk sort of simple, I didn't mention that. Okay, thank you.
Thank you very much, Kavita. So people are clapping, but it's not hearable. So are there any questions or comments from the audience?
I would have two questions.
Yes, please.
Are you familiar with graphons?
Yes.
So can you comment a little bit if you ever did something related to this? Because to me, it's a powerful format to describe convergence of
definitely.
graph limits.
Yeah. So the thing is with graphons, what graphons allow you to do, they're looking at the dense case. So in graphons, the average degree of the thing is of order, n squared. So you want, you have to have it of order n. Whereas here, and it goes to infinity, what graphons do that, sort of the standard mean field don't allow you to do is they allow you to capture heterogeneous interactions. So, you put it on the, the graphon and 0, 1, but you need dense graphs. And many, so it's of course powerful when you think you're underlying, and I didn't have time to show you, but you can take many real world networks and you try doing mean field or graphon, and they don't necessarily capture. So there are, of course, a large class of things. If you believe that your graph is dense in a suitable way, then you should use graphons. But if you don't, then there was no alternative frameworks of what approximations you can use. And so what these do is actually look at the sparse setting and have an alternative way of approximating that. And so this allows you to study both the large deviations as well as that in that case. So that's the difference, whereas you don't have that growth. And graphons don't work even when you have, which in cases when our theory also doesn't apply. For example, when you have growth of the degree of vertices are still going to infinity, but they're like n to the alpha. They're not, they're not of order n, or log n or something. So this is sort of complementary. It's looking really at the sparse graph regime, and we can allow heterogeneous interactions, as I mentioned at the last, in the end. I just didn't have time to, I didn't want to make things more complicated to put in that notation, but it's in the paper.
Okay, thanks. And the second question would be, do you think these theorems and results can be extended to higher order interactions, like more in general hypergraphs, or more in particular to simplicial complexes or something similar?
Yeah, thanks for the, I have thought a little bit about that, but haven't worked. But so one thing is, of course, we don't need pairwise. We can actually depend on the entire neighborhood. So I do think that this can be extended, but still in the sparse setting, right? So if you believe that your graph is sparse, I believe that you could do some extensions there. Yes.
Okay, thanks.
Thank you.
So there is a question in the chat, Kavita. If you want, I can read it for you. So I will read it, okay?
Yeah, I saw it. Okay, yeah, you can read it out for the audience. Okay. So it's the question is, can you comment? A very naive question. No questions are naive, so thank you for the question. Can you comment the possible link with optimal transport? So there is no immediate link with optimal transport at this level. But if you look at, there are questions that we have been looking at this with related to long-time behavior of these systems, which have then a certain optimal transport flavor. But this itself is not transporting the measure from one type of measure to another. It's more of a convergence result.
We have a question here. Let me give it.
Yes, please.
Yes. Thank you for the nice talk. I want to go back to the thing you said at the very end, that if you looked at the convergence statement, it also holds in a quench setup. Does it make sense to look at the large deviation principle also in the quench setup? And in that case, do you get rate function that depends, that varies in case between quenched and annealed?
Yeah, well, thank you for the question. Yes, it certainly makes sense to ask for a quenched large deviation principle, which is even more demanding than the annealed one. We have been thinking about that. It is much harder. So even just look at the IID setting and the quenched. So let me say that why is the quenched harder? Maybe that gives an idea. And it's definitely something that's interesting. So I didn't mention, but we also have applications of our things to sort of statistical physics questions. And there, the quenched large deviation principle is even more interesting. And I will also mention that there are results on the quenched large deviation principle for dense graphs by I-Hsun and other people. But in this case, we use symmetry properties that we get from, so of course, we know that these graphs are not symmetric in the way the complete graph is, but you have probabilistic symmetries due to the random routing of the random routing of the graph, which is called unimodularity. Okay, so remember the graph is a random graph, so it has some probabilistic structure, and that random graph has some probabilistic symmetries that one exploits in order to get the large deviation principle. And that's just a question in terms of why the techniques won't directly apply. It doesn't mean that they should not be a large deviation principle, but I'm just saying that it would require some new ideas and new techniques, and it's certainly a very interesting thing to do.
Thank you.
Thank you. So let's see if there are...
question.
Ali, please.
So yeah, regarding the degree of the vertices, like, is it possible to relax this condition of boundedness, for instance, allow the degrees to grow sublinearly, for instance, n to the power of alpha, or alpha is positive and smaller than 1, or is it rather than just alpha equals 0?
Yeah, so, at some level, we're all trying to approximate finite graphs, actually, right? So a priori, one doesn't know whether this is a dense, you might know it's not complete, but you don't know whether it's a dense sequence or a sparse sequence. So you can embed any finite graph into a dense one or a sparse one. And so you really have to, unless you have quantitative bounds, which you do in the dense due to a lot of work by different people in the diffusion setting, like including Lacker and others, Javan, lots of other people who've done sort of quantitative versions of understanding this convergence. But you don't, so my answer is, you have to ask, okay, why would I be interested? How do I know that it's sublinear? So you have to find sort of a graph ensemble where neither the mean field is a good approximation, nor is the sparse case. Because we have examples where for a finite graph, the mean field is not good, right? And in many cases, it is very good, of course. And the whole point of this is to understand when you should use this other sparse as opposed to the mean. Now, it could be that there's an intermediate regime when neither of them do well, right? And you have to use some other approximation to enter the alpha. There you cannot use graphons, but there are other notions of convergence of graphs, where the degree is going to infinity, but it's not uniformly bounded. Those are the theory there is less clean. So there are various ways of various results by Chase, Westerkombe, and Borgs and others, Lovash, etc., who have these things called sparse X's. Like instead of graphons, you use graph X's and sparse X's. And so people have done things on just static such graph convergence. And there's also this notion of LP convergence of a graph, which again works for the sparse regime. But I don't think that, people have looked at dynamics on that. To my knowledge, maybe somebody has. And the question is, can you do that? Does it give you a limit that actually is tractable and can provide a third alternative approximation that should be used in some settings when neither our sparse approximation or the dense is valid?
Okay, thank you. Thank you very much.
So let's see if there are no more questions. Thank you again, Kavita, for accepting this invitation. And we see each other same place next Wednesday. Thanks again. Bye, everyone.
Thank you for the invitation, and thanks to the audience for all the questions. Thank you. Bye.